function from the plane R2 to the real line R is simply a rule which takes each point of R2 and assigns to it a point of R. So each point with coordinates xy maps to a real number f of xy. For example, each point xy could map to the real number x squared plus y squared. Now, how would you draw the graph of such a function? Well, let's first look at a case you're familiar with, a function from R to R. For example, when f of x equals x cubed minus x, the graph looks like this. That is, for each distance x from the origin, the height y is just the image value f of x. And we use the same idea for a function from R2 to R. We again use height for the codomain, but for the domain we have to use position. So instead of distance along a horizontal x-axis, we use position on a horizontal plane. And the graph turns out to be a surface. For each position xy, we use the rule f to obtain the height of the surface. And if we do that for every point xy, we get this shape of surface. Well, we've cut it off here with a vertical slice, but it really goes upwards indefinitely. That's because as we take points xy further and further from the origin, the height, that's the value of x squared plus y squared, keeps on increasing. Well, what we've actually done here is to represent our function as a set of points in 3 space. And if we call this axis the z-axis, then a typical point on the surface has coordinates x, y, and z, where now z, the height, is constrained to equal f of xy. Well, one way of appreciating such a surface is to take horizontal sections, that is, curves in the surface, like this top rim, that are cut off by horizontal slices. Now, this section is at height 4, and it's a circle. That's because the section at height 4 is vertically above the set of points on the plane that are mapped by f to 4. And these points satisfy this equation. That's because f of xy is x squared plus y squared. Now, this is, of course, the equation of a circle of radius root 4. That's 2. So the section at height 4 is a circle of radius 2. Well, what happens if we look at a different height? We get a different circle above yet another circle in the plane. And if the height of the section is k, then the equation of this circle is x squared plus y squared equals k. That's a circle of radius root k, and we call such circles contours. In general, the meaning of the word contour is the same as the maps of mountains and valleys. That is, it's a curve in the plane that's vertically below a section of a given height. Well, as a matter of fact, the easiest way to construct such a surface, and the way we constructed this one, is first of all to work out the contours, and then to raise them to a suitable height to make a section. If we increase the value of k, the radius of the contour circle will increase, and so will the height of the section. And if we fit the sections together continuously, we obtain the surface representing our function. Let's look at some more examples. For instance, the function xy maps to x plus y. The contour for a given height k is given by the equation x plus y equals k. So this time, each contour is in fact a straight line at 45 degrees to the axes. And the section of the surface corresponding to this contour line is a copy of the line lifted up to a height k. And if we vary the value of k, we'll get a family of parallel contour lines, and the height of the section will vary. And when we join up the sections continuously, we get a sloping plane as the surface representing our function. Well, what we've actually done is this. We've taken segments of the contour lines, which really extend outwards indefinitely, as does the surface, which also extends upwards indefinitely. And here, these contour lines correspond to negative height. So the surface continues below the xy plane like this. Well, this function added the coordinates to give x plus y. So let's have a look at the function that multiplies coordinates. That function is represented by this surface, where we've taken the values of x, y, and z between -2 and +2. Really, it extends outwards and upwards indefinitely, at least in this quadrant and in this quadrant, while in these two quadrants it extends downwards and outwards indefinitely. Well, I'm not going to say much about the contours, only notice they come in two sections. In fact, it'll turn out that they're hyperbola, and we call any surface of this shape saddle-shaped. Well, that's three examples of functions from R2 to R. What about the other way round? A function from R to R2. A function mapping each point t of R to a position on the plane. Well, a position, that is a point of R2, has two coordinates, say f1 of t and f2 of t. For example, f1 of t could be 1 minus a half t, and f2 of t could be 1 plus a half t. Well, just like functions from R to R, will represent the domain along a horizontal axis with the codomain perpendicular to it. But this time, the codomain is a plane. Like this. I've marked on the plane the value of the function for t equals 0. You see, 0 maps to the point 1, 1. So, here's 1, 1. Well, what about other values of t? Say t equals 2. Well, we'll get 0 for the first coordinate, and we'll get 2 for the second coordinate. So 2 maps to the point 0, 2. So now what we have to do is we have to take another plane, crossing the t-axis at t equals 2, and on this plane we have to mark the point 0, 2. And then we have to do it for all other values of t. Well, we've got an animation that does just that. For each value of t, the function specifies a position on a plane. And if we join up the positions continuously, we get a curve in space. Well, in this particular case, the curve is a straight line extending indefinitely. though we've only shown the segment starting from t equals minus 4 and going to t equals plus 4. Well, in a moment, we'll be looking at a curve that really is curved. But first of all, let's look at this in rather more detail. Remember, a function gives a value f1 of t for the first coordinate and a value f2 of t for the second coordinate. So f1 and f2 are functions from R to R, and in this particular case, f1 maps t to 1 minus a half t. Well, we call these two functions the coordinate functions of f. Well, can we somehow use this representation and split it up to get pictures of the coordinate functions separately? In fact, we can, because concealed in this model are the graphs of both coordinate functions. And to see the graph of the second coordinate function, we have to look straight on to this side. You see, for each distance t, the image position has x-coordinate and y-coordinate, and the y-coordinate gives the height of this line above the t-axis. Now the y-coordinate is just given by the value of the function f2. So if we think of this view projected onto the ty plane, we see f2 represented as height against distance. The graph of f2. So that's f2. And if now I take this horizontal face and tilt it towards you like this, this view gives the graph of f1, since now the height of the line above the t-axis is given by the x-coordinate, and that's just the value of the function f1. So f1 is represented as height against distance. So, by looking at this three-dimensional representation from appropriate angles, we can get the graphs of both the coordinate functions. And there's a third useful way of looking at this. That's straight down the t-axis. This is important. This straight-on view of the xy plane gives the set of image positions in the codomain R2. We call this set of image positions the path of the function. In fact, instead of building a three-dimensional model of the function, you could simply draw its path like this as an alternative representation. The only problem is you can't see pictorially which values of t map to which positions on the path. But you could recover some of that information by marking in a few of the image points and identifying them. What we've really been doing here is thinking in terms of our original domain-codomain diagram. But it's actually quite common to represent the function just by its path, with a few positions identified. Let's now look at another example of a function from R to R2, this time starting from its path. A circular path of unit radius. Once again, to specify the function, we need to specify which values of t map to which points of the path. For example, let's take the function which maps the point 0 to the position 1, 0, and any point t to a position which is a distance t anti-clockwise along the path. So that's our function pictorially, as a path. But what is it algebraically? That is, what are the coordinate functions f1 and f2 as expressions in t? Well, how do we represent this function in 3 space? Well, we take the t-axis out here, and for a distance t outwards, the image position is a distance t around this circle. So, as we come outwards a distance, we travel a similar distance around the circle. And what we end up with is this spiral. Well, here's the xy plane, and here for t equals 0 is the point 1, 0. And as t increases, we come forward in an anti-clockwise manner, and as t decreases, we go backwards in a clockwise manner. Well, what about the coordinate functions? That's these functions f1 and f2. Well, let's look at their graphs. We know that to see the graph of f1, we have to look straight down the tx plane, like this. And we get a curve that looks something like a cosine or a sine curve. But notice that when t equals 0, the height is 1. So it looks more like a cosine curve. And what about the function f2? Well, we have to look straight down the ty plane, just like this. And here, for t equals 0, the height is 0. So it looks rather like a sine curve. So, just by looking at the shape of the graphs, we would guess that the coordinate functions are something like the cosine and the sine function. And in fact, this turns out to be exactly true, and we'll see that by looking at the path. The image position f of t has x and y coordinates f1 of t and f2 of t. So f1 is cosine and f2 is sine, because that's how you define sine and cosine. You go an arc length t around a unit circle, which means the angle is t radians. And the horizontal coordinate is cos t, while the vertical one is sine t. So, we've seen two ways of representing a function from R to R2 pictorially. Either by constructing its curve in 3 space, or by drawing its path in the codomain R2 and identifying an arbitrary image point. So, that's functions from R to R2. And earlier, we dealt with the reverse situation. A function from R2 to R, which we represented as a surface. The final type of function we'll look at is one from R2 to R2. Each position xy in the domain gets mapped to a position in the codomain, a position which has 2 coordinates. So again, we need 2 coordinate functions, each one mapping a point xy in R2 to a number in R. Here's an example. f1 maps the point xy to the number 1 plus x minus 2y over root 2, the first coordinate of the image position, and f2 maps xy to x plus 2y over root 2, the second coordinate. Well, how do we represent such a function? Well, what we do is we stick with our original domain codomain diagram, and we look at a suitable sample of points in the domain, and we see what they map to in the codomain. So, how does this function map points? Well, it's an affine transformation, and we can write the image of a typical point xy in matrix notation like this. It's a dilation in the y direction by a factor of 2, followed by a rotation through 45 degrees, that's this matrix divided by root 2, followed finally by a translation of 1 unit in the x direction. Now, what sample of points are we going to take? Well, we're going to take the points in this grid. So, first of all, we have to operate on them by a dilation of a factor 2 in the y direction. And what we get is this grid. So, first of all, the points in this grid go to this grid. Now, how about the rotation through 45 degrees? We have to move the grid to here, and finally the translation through 1, we move the grid to here. So finally, the points of this grid are mapped to the points of this image grid. Well, this gives us a very good representation of the function, because we can find the images of intermediate points by looking at the intermediate points on the image grid. Well, that was an affine transformation, and it mapped straight lines to straight lines. But not all functions from R2 to R2 do that. For example, suppose f1 of xy is x squared minus y squared, and f2 of xy is 2x times y. It turns out that vertical and horizontal lines both map to parabolas. You'll read more about this function in the text, where you'll see it actually represents a function from the complex numbers to themselves. It maps z to z squared. Well, that's all the types of functions I want to deal with, and I'm going to go through them all again in this last item while I give a brief preview of continuity. Well, continuity is the subject matter of the next unit and of the last section of this unit. And for all the functions we've been looking at, continuity means what you intuitively think it means. So, for instance, this function from R to R is continuous because its graph looks continuous. It's unbroken. But when we actually get down to details, what we'll have to do is we'll have to look at intervals in the domain and their images in the codomain. In fact, this unbroken interval in the domain maps to every height between this one, and so its image is an unbroken interval in the codomain. Well, this happens in general. This is a property of all continuous functions from R to R. They map unbroken intervals to unbroken intervals. When we actually get down to the details of the definition of continuity, we'll see that rather than just using one interval, we'll have to use nests of intervals. Well, now how about functions from R to R2? Well, this one looks continuous because the curve is continuous. It's unbroken. But in fact, that turns out to be equivalent to the two coordinate functions f1 and f2 being continuous. But these are just functions from R to R, and we've just talked about their continuity in terms of nests of intervals. Well, in this case, the coordinate functions are cosine and sine, and they turn out to be continuous. Now how about functions from R2 to R? Again, this looks continuous because the surface is continuous. And this time when we get down to the details, we'll find we have to look at rectangles in the domain and their images in the codomain here. And what we'll find is that an unbroken rectangle like this maps to every height between this greatest one and this least one in here, and so its image in the codomain is again an unbroken interval. Well, finally, how about functions from R2 to R2? Again, continuity boils down to the continuity of the coordinate functions. This time, they're functions from R2 to R. And that's just what I've been dealing with. Well, that was a very brief preview of continuity. But I hope when you get onto the details, you'll find it's been worthwhile. But the major point of this whole program has been ways of visualizing functions like these. And when you get onto continuity, this visualization will certainly be useful.